Hi, I am Dr. Eli Kohlberg from Unlimited Robotics. In this video, I will talk about electric field. Electric field is defined as the electric force per unit charge. The direction of the field is taken to be the direction of the force it would exert on a positive test charge. The electric field is radially outwards from a positive charge and radially in towards a negative point charge. An electric field is an invisible force field caused by an electric charge. It is an alteration in the space, air, or vacuum around the charge. It results in an electric force that is felt by electric charges when placed close to one another. A static electric field is created when the charges are stationary and the corresponding force is known as the electrostatic force. Any other charge that enters that area will feel a force, and the original object will also feel that force, according to Newton's third law. The electric field is a vector quantity having both magnitude and direction. Electric field is defined as the electric force per unit charge. The strength and direction of the electric field are represented by electric lines or forces, or electric field lines as presented in next figure, which we can see that from a positive charge, the lines are going outwards, and for negative charge, the lines are going inwards the charge. The lines are drawn with arrows to signify the direction. For a positive charge, the field lines comes out of the charge. For a negative charge, the field lines move towards the charge. When a positive charge is placed close to a negative charge, like an electric dipole, the lines come out of the positive charge, repels, and terminate into the negative charge, attracts. Therefore, the direction of the field indicates the direction towards which a positive charge moves when it is placed under the influence of another charge. The strength of the electric field is the space surrounding a source charge is known as the electric field intensity. Electric field is a vector that has a magnitude and direction. Mathematically, an electric field is defined as the electric force experienced by a point charge. The following equations give the electric field vector. E, which is the electric field, equals F divided by Q. F is also a vector, the force. And thus, F equals Q times E. The corresponding scalar equation gives the magnitude formula E equals F divided by Q, where E is the electric field in Newton over Coulomb, or volt over meters, F is electric force in newtons, and Q is electric charge in Coulomb. The electric field can be calculated using Coulomb law, that F equal 1 over 4 pi epsilon Fs times Q1 Q2 divided by R squared is also equal to Ke times Q1 Q2 divided by R squared, where Q1 and Q2 are magnitudes of the two charges, R is the distance between the charges, epsilon 0 is permittivity of free space, which is equal to 8.85 times 10 to the power of minus 12, and Ke is 1 divided by 4 times pi times epsilon 0, which is equal to 8.987 times 10 to the power of 9. By definition, the electric field is the force per unit charge. Therefore, Q1 equals Q and Q2 equals 1. Then electric field will be E equals F divided by Q, which is equal to 1 divided by 4 pi epsilon 0 times Q1 Q2 divided by R squared times 1 divided by Q2, which is equal to 1 divided by 4 pi epsilon 0 times Q1 divided by R squared. Since we have only one charge, we can write it as 1 divided by 4 epsilon and pi epsilon 0 times Q divided by R squared. So this is the electric field magnitude. Thus, the strength of an electric field depends on the magnitude of the source charge. When multiple and different charges exist, field lines start on positive charges and end on negative charges as presented in the next figure. When only positive charges exist, the field lines will not cross each other as is presented in the next figure. When we have positive and negative charge, the lines come out of the positive charge and ends in the negative charge. When we have two positive charges, the lines of the field, they do not cross each other. The electric field is said to be uniform if its value remains constant over a region in space. Its magnitude does not depend on the displacement and the field lines are parallel and equally spaced. Example, a uniform electric field can be created between two charged parallel plates, also known as a capacitor. The electric field lines come out of the positive plate and terminate into the negative plate as presented in the next figure. Example, an electric force of 8 newtons is acting on a charge of 3 microcoulomb at any point. Determine the electric field at that point. Answer. Given F equals 8 newtons, Q equals 3 microcoulomb, which is 3 times 10 to the power of minus 6 coulomb. According to electric field equation, E equals F divided by Q, which is 8 newtons divided by 3 times 10 to the power of minus 6 coulomb, which gives us that 2.67 times 10 to the power of 6 Newton over Coulomb. Another example, a small charge Q equals 4 millicoulomb is found in a uniform electric field E equals 3.6 Newton over Coulomb. What is the force acting on the charge? Given E equals 3.6 Newton over Coulomb, Q equals 4 microcoulomb, which is 4 times 10 to the power of minus 3 coulomb. According to electric field equation, F equals Q times E, which is equal in this case to 4 times 10 to the power of minus 3 times 3.6, which gives us 14.4 times 10 to the power of minus 3 newtons. This is for now. Thank you for being with me in this video. I hope to see you in the next one. Bye bye.